Haslop. So we'll start with Paul Heslop, and he'll tell us about correlation functions of half-BPS operators and equals four superior.
Okay, thank you very much. And I'd like to add my thanks to the other speakers for this wonderful conference in this wonderful city. It's been great fun being here. So yeah, I'm going to be talking about correlation functions of half-BPS operators and equals four young males. So I'll first review work done in a few papers over a few years with Burkhard Eden, Gregory Korczynski, and Emery Sokachev, where we looked at a specific correlation function of so-called energy momentum multiplet. And then some work in progress. Well, it's basically done. We need to iron out a few details, should appear soon, with Dmitry Chicherin, James Drummond, and Emery Sokachev, where we generalize the story at three loops for all half-BPS operators. So I've just spoiled the punchline really, but to begin with we were less ambitious, but it turned out that we were able to find all the correlation functions in using a new result, which I'll come to. Okay, so we're slightly missing the left hand, but it should be okay, I think. So I'll begin by telling you precisely what I'm looking at and why we're looking at it. And then I'll go on to review the story about the stress energy multiplet, and then I'll discuss the method that we have for determining the more general correlation functions. And the point is, so although this is not really amplitudes, it's quite closely related to amplitudes, as we'll see at various points. And in particular, some of the techniques are the techniques that are popular for amplitudes. Although here they're, in some sense, seem to be even simpler, at least for the 4-point case here. So basically, we're using symmetries, analytic properties, planarity. I'm going to be discussing large N throughout this talk. If I forget to say it, then it's implicit. And the OPE in several different ways, which is sort of related to the analytic properties, but also gives us more information. So I'll give you the ingredients, and I'll go through them step by step, and then I'll give you the results at the end. So the main point here is we're just discussing integrands. So we're just discussing rational functions, albeit quite big and complicated ones. But it's a fairly simple setup, really. But at least at three loops, which is as far as I will go, we know what all the corresponding integrals are. They're all known analytically. So although we only explicitly determine the integrands, we know the integrals, so we have the full analytic answer as well. Okay. Okay, I don't really need the slide of this audience. So I'm doing N equals 4 young mils, and hopefully you're all happy with the motivation for looking at that theory. It contains a gauge field, 6 master scalar fields, and 4 fermions. So what correlation functions am I looking at in this theory? So I'm looking at correlation functions of gauge invariant operators. These were mentioned in Gagnan's talk earlier, a specific operator of this type. So in general, gauge invariant operators, I just take any of my fundamental fields and get rid of all the hook together all the adjoint gauge indices in some way. A large N is the single traces which are leading. And more specifically, I'm going to be discussing a particular type of gauge invariant operator. So first of all, let me take my 6 scalars and put SU4 indices on it. So if this is antisymmetric, there are 6 of these. The first thing I'm going to do is, in order to get rid of the indices, I use an internal variable y. So y is taking, it's a 2 by 2 matrix, if you like. So A goes from 1 to 2, A prime goes from 3 to 4. And I package together all of these phi ij's into a single scalar object which now depends on 2 variables, x and y. So x, as we saw earlier in Minkowski space in some of the talks, I think it was a 2 by 2 matrix. Y is really the same sort of object. The only difference is it lives on a compact space, but it's really the SU4 acts on the y's in exactly the way as the conformal group acts on the x's. Okay, so then I have my scalar and it's packaged together in one object, and I can just deal with this without having to deal with all the indices.
So why does it terminate? I mean, what's it terminate?
Yeah, again, that's related to the fact that it lives in a compact space. So and it's an analytic field on a compact space. So if it was just a function, it would be constant, like on a hemisphere. It has a charge under this. So if I go from the southern hemisphere to the northern hemisphere, the charge is 1/4 squared. If you figure out the details, you find it has a.
So it's a constraint theory.
Well, it's constrained. It depends how you view it. It's unconstrained. It's an analytic field of a certain weight, certain charge on a compact space. If you want to view that as a constrained field, you can do, I suppose. Okay, I mean, if it was just the Riemann sphere, I can go from y to 1/y. The field transforms also with a charge y. So it has to be analytic in y and analytic in 1/y, and therefore you only get a certain terminating result. Okay, so that's how I package together the scalars. Then the operators I'm looking at are just traces of products of this scalar. And this automatically puts them into the symmetric traceless representation of SO6.
Are those some kind of projective superspace?
Yeah, it's a harmonic superspace or analytic superspace. But I'm sort of hiding the details here. I mean, you can add thetas into this game. But we only really need this part of it for this talk. And we want to compute the correlation functions of 4 of these operators, of arbitrary charges, K1, K2, K3, K4. Okay, so this is, as I said, it's a symmetric traceless product of the 6 scalars. So, for example, for the experts, Kanishi is not here, but the stress energy tensor is in this product traceless first square. Okay, so.
No normal dimensions.
Exactly. So the actually maybe I say that here. Yeah. So the anomalous. Okay. So let me go to this slide. So the operators themselves are all half-BPS and therefore protected. So they themselves have no anomalous dimensions, which means the symmetry, the conformal symmetry, acts on the correlation function in a naive tree-level way. However, inside the correlation function, it hides the anomalous dimensions of all sorts of unprotected operators. They're hiding now because I can do an OPE and get an unprotected operator. I can do an OPE of 2 of my operators and have an unprotected operator as the third. Okay, so the thing itself has nice symmetry properties. It contains within it 3-point functions of a whole slew of operators. Half-BPS, half-BPS, and a third. Okay, so and these guys, from ADS-CFT point of view, it's interesting because these are all essentially Kaluza-Klein, where you get by Kaluza-Klein supergravity on the S5 sphere. So the first one, the stress energy tensor O2, is related to supergravity on ADS5. But if I'm interested in supergravity on ADS5 cross S5, then I've got a whole infinite expansion by expanding the S5 there. And that's what these OKs correspond to. Okay, so it contains all this information, and recently these people have come up with a way of computing the 3-point functions sort of directly, and so it's become interesting to compare with the results here and to see if they agree or not. Come back to that at the end of the talk. Okay, and then of course here I should mention the further motivation, which is the relation to amplitudes. So these correlation functions, not necessarily all of them, but many of these correlation functions contain within them the amplitude according to this formula. Here, this is the amplitude divided by the tree level amplitude squared. And this should be thought of as an integrand level identity, and we don't have to worry about divergence and things. now it's not quite true for all correlators. It's only true where this left-hand side makes sense, which means that I have to have some tree level diagrams which only contain this square. So that's not always possible if I have high enough charges. You cannot find any tree level diagram which only contains the square, and then the left-hand side doesn't really make sense. But for many of them, I can do this, and certainly for the 2222 one, which is the one we've looked at in most detail in the past, this is correct. And there's a lot of interaction between the two sides. So the correlation function has some hidden symmetries I'll talk about soon, and gives you information about the amplitude. But similarly, if people are able to figure out the 4-point amplitude, as they have done in the past, we can easily go backwards and get the corresponding 2222 correlation function. Okay, so that's what I'm going to talk about for the next few minutes. The 2222 correlation function. This is the stress energy multiplet. So to summarize what we've found there, and I'll discuss in a little bit more detail on the next two slides, there's a hidden symmetry between external variables, 1, 2, 3, 4, the 4 points here, and loop variables, which enables you to uniquely fix, well, I say uniquely, there's an overall, up to a single overall coefficient that you can fix the guy up to 3 loops. Then 4, 5, and 6 loops and beyond, it's still quite constraining. You only have 3 constants to fix, 7 constants to fix, and 36 constants to fix. And then we were able to fix all these constants basically using a trick from Jake and Mark and their collaborators, where you can, well, essentially the story there is that you realise that the log of the amplitude has a reduced divergence, which you could analyse at the integrand level. You can see where the divergence comes from, and then use that to restrict your integrand, essentially. So using this technique, we could then determine all these constants and find the correlator up to 6 loops. So let me just repeat a little bit this story. Many of you have probably seen it before, but the point here is that this correlator is given in terms of a single function of x's. So I write this. I'll show you precisely how the relation between this and this in a moment, in a more general context. But basically, I just have a function of 4 external variables, x1, x2, x3, x4. This is just 4-dimensional space-time. And then L external variables, so from 5 up to 4 plus L. And there's a hidden symmetry which says that the function has to be totally permutation symmetric in these 4 plus L variables. So you expect it to be, or you can define it to be permutation symmetric in the integration variables, and it's also permutation symmetric in 1, 2, 3, 4 because of crossing symmetry, but you don't expect this sort of hidden symmetry between internal and external variables. So that comes from superconformal symmetry, and if I represent this function graphically in the sort of standard way, so these functions have a conformal weight. They're conformally covariant, which essentially means that only xij squareds can appear, xi minus xj squared, the Lorentz product. They have a certain conformal weight, which you can just analyse from the correlation function. They have no double poles, which comes from the OPE. Again, many of these things we'll see again in more detail shortly. And then I can just graph the function. So this corresponds to looking at degree 4 graphs on 4 plus L points. But you're allowed more than degree 4. So degree 4 corresponds to the conformal weight 4, but you can also get conformal weight 4 by having a numerator and then having a higher power in the bottom. So it's degree greater than 4, but then with some numerators to get the weight back. Okay, so then at one loop, so this is secretly just a box function. It doesn't look like a box function, but essentially a box function in dual momentum space looks like this. And then all I've done is I've put all possible external lines onto that. So this is 1, 2, 3, 4 external lines, 5 in the middle. And if I put all external lines there, including that one and that one, then I get this graph. So that's kind of trivial. The non-trivial case is the two loops. This is the full answer, and it's just given by one graph, and I sum over all permutations of the point, so I don't really need to label it. I put some labeling on, and then I sum over the permutations of the labels. So, and then at 3 loops is given by this graph. These blue nodes denote the fact that these are degree 5, and that corresponds precisely to this 4th power here. So most of these guys are actually just deleting propagators. Here on the denominator I've got all propagators. So these delete propagators. But here I've done too much. I've deleted a propagator and then there's a leftover propagator. So I've got, there's a genuine x12 squared, which is a secret numerator line from the blue node to the blue node. Okay, so the graph gives you all the information, and if I wrote this all out, I'd get a series of graphs. It would contain the 3-loop ladder, the tennis court, 1 loop times 2 loop, and then a couple of the extra ones called easy and hard, because of how difficult they were to find or not. Okay, and 4 and 5 loops, you can write it down. So it's quite a compact writing. But again, all of these graphs contain within them a sort of slew of different integrals, really. Okay, so that's the story for 2222. And what I want to talk about now is going beyond this 2222 case. So, so for arbitrary charge correlation functions, K1, K2, K3, K4. So beyond this particular case, so in the past, in a sort of 4 or 5 years or so after ADS-CFT, they were computed basically using Feynman diagrams in various forms, either in harmonic superspace or otherwise. So many of them, but not all of them, have been computed at 2 loops, and so now there's nothing beyond 2 loops. So we wanted to sort of start from scratch and use some of the ideas that I've just discussed to try and get some of the higher charge correlation functions, especially motivated by this recent activity on the 3-point functions. So in general, we're going to lose this hidden symmetry. The hidden symmetry is specific to the O2, and it's related to the fact that the 2 contains the Lagrangian, and the loops are you can think of as Lagrangian. I'll show you that in a slide in a moment. But, so there are some correlators which have a bit of hidden symmetry. So if I have KKK2, that will have a L plus 1, SL plus 1 symmetry. But in general, K1, K2, K3, K4, if none of them are 2, then there's no hidden symmetry. So that thing which was sort of very crucial in the previous case is essentially gone. We also lose the y independence. So I started off telling you the thing was a function of x and y, and then I said that in fact for this guy I only need to consider a function of x. So that fact is gone as well. Okay, but nevertheless we can see how far we get. So this is the recipe for computing these guys. So well, we start off right at the start is the fact that we have a rationally conformally covariant function. So it's a function only of xij squared as before, but also of yij squared. Well, that's from SU4 symmetry, but it looks very much like the conformal symmetry. Now, superconformal symmetry, which is what we used at the 2222 case to say that it's only a function of x, does give you some restrictions. So I'll show you what restrictions that gives. Analytic properties. So I've called this OP. We basically use the OPE 3 times in different ways, and sort of in various ways. So first of all, we just use it to see what the leading divergences are, to see what the pole structure is like. So I call that analytic properties. We use planarity, which is very powerful. And then I use the OPE again. And now this is a recently found thing which I will discuss. It relates correlators of different weights to each other. And this is probably the main new input that's allowed us to quickly get all of the correlation functions. So this relates different charges with the same loop order. And then finally, using these three, it turns out we actually get everything up to just two constants. And we've got two constants to fix. And we need something else to fix the two constants. And there's this so-called Euclidean OPE constraint, which can fix those for us. This one, it relates the same charge with different loop order. Okay, so this is my correlation function. I'm just defining it, the integrand to be gk1, k2, k3, k4. As I briefly started to mention, the integrand itself really is a physical object for us. We hear, a lot in the amplitudes about the planar amplitude being, in some sense, an object in its own right. And here you can really make a very concrete sense of that. It's just a correlation function at tree level. So I can get this 4-point correlation function by taking a 4 plus L point correlation function where the L points are Lagrangians, but then the Lagrangians sit in the same multiplet as the O2. So I can get one from the other by considering this correlation function at tree level. Okay, what this basically means, though, when it all comes down to it, is that this object is simply a rational function of xij squared and yij squared. That comes from conformal symmetry and SU4 symmetry. It's homogeneous of degree k1, k2, k3, k4 in the y's, and of minus k1 to k4 in the x's, as well as, it depends on these x's at the internal points, and it's degree minus 4 in all of those. Okay, so that's all we have to consider. Now, superconformal symmetry. So I won't go into the details of where this formula comes from. So this is the same formula as at the 2222 case, essentially. This correlation function factorizes into an object which I just call R times another object. This you can sort of think of, if you like, as a bit like MHV amplitudes factorizing into a sort of a tree level bit and the interesting bit, if you like. So this R1234 is independent of the coupling. It's just that. It's just some complicated polynomial in x and y. And then, so it's the h that we're really interested in. And the advantage of that, in terms of the calculation, is simply that now this has soaked up some of the weights in the x's and y's. So now we're just looking at an object that has the weights of a correlation function with charge 2 less, essentially. So now our charge is k1 minus 2, and so on and so forth. Okay, so going a bit further, now I know the weights of the h, in particular the y weight. The y's only occur polynomially because they were just generating functions for the scalars, really. So the left-hand side is polynomial in y's, the right-hand side is polynomial in y's. So I can just write down the general polynomial in y's of that weight. So here I just write down arbitrary products of yij squared. There are only 6 of these, y12, y13, y14, y23, y24, and y34 squared, with arbitrary powers. The powers have to add up to ki minus 2, that's the homogeneity. And then the coefficients of these guys I call f. And now they only depend on the x's, just as for the 2222 case. So I've deconstructed the problem into just finding a bunch of functions of x. And these functions of x have nice properties. So these are the building blocks, if you like. So firstly, they're conformally covariant. Now they have weight minus 4 at each point. that's basically because I've added this xij squared here, which I didn't have to, but that has the effect of making them have weight -4 at each and every point now, internal and external. And now going back to the previous case, the 2222 case, we noticed that that also obeys this formula, but here the sum of all the b's has to be equal to 0, which the b's are positive, so there are no, this factor is basically gone, and I'm just left with a single function. That's the function that we discussed previously. Okay, so the previous case, 2222 case, there was just one building block function. Now there's just a few building block functions. Okay, analytic properties. So by studying the OPE carefully, you can see that having removed this 1 over xij squared to the power b, this function now has at most simple poles in xij squared. Now that's of course crucial now, because if you could have object powers, then you wouldn't have a finite problem. But now I know what the pole structure has to be, and I can write my function as a polynomial divided by all possible xij squareds. And now I just have to find these polynomials. And there's a finite basis for those. So basically, we've reduced the problem down to finding a bunch of numbers. We've got a finite basis, we just have to find the numbers of this basis now. So that's kind of what you want really from any problem, to reduce it down to just finding some numbers. Okay, so that's very good, but still the basis is quite big. I don't know, maybe I'm a bit embarrassed in this audience to say that 82 free coefficients is big. I mean, you guys are dealing with... this is probably tiny, but anyway, we need some way of determining them, whether it's big or not. So the first ingredient that we use is planarity. So if I look at these free coefficients, many of the things that I draw are highly non-planar. If I just draw them in the way that I said, they're highly non-planar. So what precisely do I want to say about planarity? What I want to say is essentially that each component of y squared should correspond to a planar graph. Every term, the full supercorrelator should be a planar graph. Now we know that if I was to compute this thing using Feynman diagrams, then the expressions would be planar. So then the claim is that in the process of rewriting the Feynman diagrams in a manifestly conformal way, that I don't spoil the non-planarity. So this, well, okay, most people I ask seem to not understand why I'm concerned about this point, but I'll leave it to your judgment to see whether this is fair enough or not. I suspect actually there's a way of proving it using a recently found twist derivation of these correlation functions. So far we haven't done that. So this is an assumption, if you like. But the fact that we get a consistent answer is also a powerful. It tells you that something's right there.
Sorry, why you don't have non-planar Feynman diagrams?
I'm doing the large n limit. So if I was doing non-planar sets, you could have all sorts of stuff, and the story would be much more complicated. But in the large n limit, it simplifies.
They're operated on the inside, so they don't.
Yeah, I mean, it's not like an amplitude. It's really planar in the sense of graph theory. There's no concept of outside or inside. My operators can go anywhere, and then I can draw it on a sphere.
Sorry, so most actually the pictures you drew were planar embeddings, but interestingly the one loop example was K5.
Very well observed. Yes. Okay. Now that's a good point. So I have to multiply it by this.
Yeah. Okay.
Now, so the correct statement is every term, like I pick a y component, then that graph has to be planar. So the graph that you saw that was non-planar times this has to be planar.
Okay.
Now, but every single term has to be planar. So I have to be able to multiply by a different possible x squared, and it's still